Okay, let's have a look at paper one from the externals from last year. Obviously, this is combined with the multiple choice to do the entire paper. Okay, so question 21. Straightforward recall. Glucose is an example of a monosaccharide. Hopefully, that shouldn't have presented any problems. Nothing to understand, just learning. Starch and cellulose are both polymers of glucose. Compare the structure of these two in terms of glycosidic links. Starch and cellulose use different forms of glucose. Starch uses alpha glucose and cellulose uses beta glucose. So that's the first thing you need to say there. And then starch forms a linear polymer due to the 1 to 4 glycosidic links. I'll show you the structure in a second. This is what we call amylose. And then occasionally, every, say, 20 or so glucose units, you get a branch, and then you get a 1,6 glycosidic link to give the other form amylopectin. This is used mainly for storage because there are more ends on a branch structure, meaning more access to the glucose when it's needed. Cellulose only forms a linear polymer. In your data book, they'll give you alpha glucose. Don't worry about the D, it's not important. It's alpha because on the number 1 carbon here, the one that's to the right of the OH points down. In beta glucose, that OH points up. The ring prevents you rotating so that these effectively keep the OH in those positions. When starch forms, the OH on the number 1 carbon links to the OH, this one here, on the number 4 carbon of the neighboring molecule. That eliminates water in a condensation reaction and forms the 1,4 glycosidic link. Now, cellulose does the same thing. Cellulose has the OH pointing up, and again, the OH on the number 1 links to the OH on the number 4. But for those two OHs to get at each other, you've got to flip the next glucose through 180 degrees. So the CH2OH pointing up there will point down here. Then you'll have to do the same again and again. So the CH2OH points up, then down, then up, then down, then up, then down, and so on. This gives an incredibly straight chain with lots of OH groups, which allow cellulose to bond very, very securely to its neighbors. And this is why it's so hard and so rigid. Question 22 is acid-base. What we have here is an indicator, phenol red. Here is its acidic form. Here is its basic form. You will notice that there are no charges here. There's a negative charge there. It's not one of the best examples to illustrate this because clearly there was no H there at the start. The H has come from there, and then the entire structure has rearranged to give this ion. However, all we're asked to do is identify the conjugate base. Here's your acid, and this is what you would circle as the conjugate base. Phenol red at 50 contains this concentration of the conjugate base. That means it'll contain that concentration of the H plus as well, because when it forms the base, it loses an H plus at the same time. So they will have exactly the same concentrations. If you're working out Ka, you will square that concentration effectively. So this is the conjugate base. This would be the H plus, and then you divide by the concentration of the acid. It says at equilibrium, there's your concentration of acid. So you divide that by 0.034. I'm assuming Ka is nice and easy. A minus times H plus over HA, and there it is there. Pop in the values, work out Ka, and then pKa is simply the negative log of that. Now, the next question is going to ask you about colors of the indicator and so on. Please realize this. The pKa of the indicator at 5.9 is effectively the changeover point. It's the point where the red of the conjugate base and the yellow of the acid are in exactly the same concentrations. So what we probably see at that point would be an orange color. Now, any pH below 5.9 would be yellow, and any pH above 5.9 would be red. Now, that's not strictly true, of course, because an indicator has a range. So what we need is obviously to know exactly how big the range around 5.9 is. And then what you'd see basically is there we are, it says phenol red changes color at that pH value, but when the pH is below that, it'll be yellow, but you may see a little bit of red there. Of course, remember, there's a range. So at 5.8, it wouldn't be yellow, right? But it would be more yellow than red. And as you go lower and lower, it'll get more yellow, less red. So the orange color will get kind of more yellow. And then if you go the other way, the orange color would become more red. Now, once we know exactly what the range is, and it's usually about 1 and a bit units, so probably by the time you got down to about 5, you'd be looking at definitely yellow. And if you got up to about 7, it would be definitely red. But what you have to say is effectively what they've got here. So pH below that, it'll turn yellow. pH above that, it'll turn red. Electrolysis of molten sodium chloride is simple because the only ions present are sodium ions and chloride ions, and they will discharge as sodium and chlorine. Notice it's got Na liquid because molten sodium chloride would be hot enough to melt the sodium. In fact, molten sodium chloride is over 800 degrees. Sodium melts at about 98. So that would be very, very definitely a liquid. This, of course, would be a gas at those high temperatures. Dilute aqueous sodium chloride. Now then, this is a tricky one because what we have here, if we go to the electrochemical series, in dilute aqueous sodium chloride, we've got sodium ions, we've got chloride ions. However, water will also produce H plus ions and OH minus ions. And to decide what's going to discharge, you have to look at the electrode potential values, because the easier it is, the more likely it'll discharge. Now you can see to discharge sodium is a huge value. Minus 2.71 tells you it's extremely, extremely difficult. Whereas hydrogen, of course, is 0. So this is why hydrogen gas discharges and not sodium. At the anode, you're going to get hydroxide ions, you're going to get chloride ions. To discharge chloride would be minus 1.36. To discharge oxygen would be minus 0.4. Again, you can see why oxygen discharges and not chlorine. Okay. What it's saying here basically is sodium ions, chloride ions, hydrogen ions, hydroxide ions are all present. And then we look at the values, and whichever is the easier to discharge is the one that's going to discharge. Question 24 is showing the effect of temperature on the pH of pure water. Now remember, the pH of pure water will be determined by the H plus concentration, which we can see. Since the pH is going down, that means the H plus concentration is going up. So when you heat water, more H plus ions are formed, meaning it dissociates more. So in this equation here, the water is going further to the right when we heat it. That basically means, is it endothermic or exothermic? Well, of course, Le Chatelier tells us that any change that you make will be opposed. So if we heat the thing up, it will oppose us and try and cool down. So therefore, the forward reaction must be endothermic. To calculate the Kw at that particular temperature, all we have to do is take the 6.63, take 10 to the minus 6.63 to work out the H plus concentration, square that, because effectively every time it produces H plus, it produces OH minus, and then effectively that'll give us Kw. Incidentally, I don't know if it's going to ask it. No, it doesn't. I'll mention it anyway. If you're thinking, well, if the pH of water is going above or below 7, does that mean water is becoming alkaline or becoming acidic? That is not the case. Water is always neutral as long as it's pure. The reason being, neutrality is decided by the balance of H plus, H3O plus, and OH minus. And as long as they are in equal concentrations, then effectively the water will be neutral. Okay, so don't think water becomes acidic when it's hot and alkaline when it's cold. Water is always neutral. Okay, we are looking at another equilibrium, a gaseous equilibrium between N2O4 and NO2. You can see that we're starting with concentrations of 0.02 of this one, 0.08 of that one, and then by the time of 80 seconds, you can see that both have leveled off, meaning equilibrium has been reached. Okay, once concentrations are constant, rates are the same, equilibrium is reached. Okay, so the time at which equilibrium is reached is 80 seconds. If the temperature is held constant, what effect would there be on doubling the volume at 100 seconds? And sketch the changes that would occur to the new equilibrium. Okay, so if we double the volume, what we're doing effectively is halving the pressure. This will force this equilibrium to shift to the right, to the side where there's more gas. So N2O4 will get less, NO2 will get more. So on the graph, what we're looking to do is bring this one down and bring this one up. They're not giving you much room. So if you go up gradually and then eventually level off here, then this one needs to go down gradually and level off at half that value, because every one of those makes two of those. So if this goes up one entire unit, this will go down by half a unit. Okay, and make sure they level off at the same point. Mass and infrared spectra for an organic compound X, so the empirical formula of that, if it's a 1:2 ratio of carbon to hydrogen and a single oxygen, then you are guaranteed it's an aldehyde or a ketone. Okay, so this could be pentanal or one of the pentanones or a variety of that. There's the infrared spectrum. There is the C double bond O, the carbonyl group. There is the CH of an aldehyde. Now, the reason I'm emphasizing that is because the answer that QCAA provide is wrong. They have said that the CO, yeah, we've got that one, either aldehyde or ketone. And then it says there is no stretch in that region there. Let's read that again. No stretch in that region there. No stretch in that region there. I have no explanation for why they've done this. All I can tell you is clearly the answer is wrong. The answer they've given is pentanone. The answer that should be, now I've written this in myself, this was QCAA's answer. This is not in the QCAA answer marking guide. I've written in pentanal. The fragment at 43 would be either of those. They're both 43. Okay, which is why, of course, the 43 is such a very popular peak. There are two possible ions that can give it. And the one at 71 is simply the molecular ion of 86. Take away a CH3, which in the pentanal's case means lopping off that end one there and being left with that ion. Okay, so this is pentanal, not pentanone. Okay, we are doing a metal displacement reaction here. Identify the species oxidized in the reaction between Z and XNO3 2. Okay, so you can see that when Z reacts with XNO3, there is a coating. So this metal must be more reactive than X. And the species that's oxidized would be Z, because Z will go into solution as its ions, it will lose electrons. The oxidizing agent in the reaction between